Chapter 1. 4,000 meters of silence. In September 1985, at 2 in the morning, somewhere in the North Atlantic, a team of researchers aboard the research vessel Knorr had been awake for hours. On the monitors in front of them, gray murk drifting slowly past the cameras of an underwater robot. Nothing. More nothing. And then, a boiler, enormous, covered in sediment, but absolutely unmistakable. Then a section of deck. Then a bow rising out of the darkness, like a multi-thousand-ton ghost. Nobody in the control room shouted. Nobody celebrated. The people standing there simply stared at the screens in silence, and oceanographer Robert Ballard would later write in his memoirs that the quiet in that room was the kind of quiet you only find in one place, a cemetery. They had found the Titanic, the most famous ship in human history, lying on the bottom of the Atlantic for 73 years. And the first thing the team felt was not triumph. It was unease, because what the cameras were showing them did not match any of the existing reconstructions. The ship was not lying in one piece. It had broken in two. The bow and the stern were separated by 600 meters of open seafloor, and the metal of the hull was covered in something that the scientists had not expected to see and could not immediately explain. That was 40 years ago. Since then, dozens of expeditions have visited the Titanic. Around 6,000 artifacts have been brought to the surface. The ship has been photographed at 1mm resolution. It has been studied by military teams, scientists, billionaires, and filmmakers. James Cameron personally dived to it more than 30 times, more than any other human being on the planet. And the more people looked at this ship, the more insistently one question kept surfacing. Why have we still not raised it? We have deep water technology. We have floating cranes capable of lifting tens of thousands of tons. We have money. Over the past few decades, several wealthy individuals seriously considered raising the Titanic as a commercial venture and were prepared to invest hundreds of millions of dollars. We have motivation. Roughly 1,500 people died on board. Their story became part of global culture, and the ship itself became a symbol whose value cannot be measured in any currency. And yet it lies exactly where it sank in the early hours of April 15th, 1912. Most people, when they hear this question, assume the answer is depth. 4 kilometers sounds like an insurmountable obstacle, but it is not. Humanity has long been capable of working at such depths. The real problem is something else entirely, and it is so unexpected that when scientists finally stated it plainly, even the most stubborn advocates of raising the ship went quiet. To understand what that problem is, you first need to understand what actually happened to the Titanic, not on the night it sank, but in the 73 years afterward, while nobody was watching. And to do that, the story has to start at the beginning. The Titanic left Belfast in April 1912 as the largest moving object ever created by human hands. It was 269 meters long, roughly 3 football fields. Its displacement was 52,000 tons. Its construction took 3 years and the labor of more than 15,000 workers at the Harland and Wolff shipyard. It was equipped with everything that 1912 considered the peak of technical achievement. Steam engines producing 46,000 horsepower, a system of watertight compartments, its own power plant, a wireless telegraph room, and a swimming pool. The first ever fitted aboard a passenger vessel. The British press called it unsinkable, though the White Star Line itself never officially used that word, a detail that history eventually rewrote. On April 10th, 1912, the Titanic departed Southampton on its first and only voyage to New York. On board were 2,224 people, passengers across all 3 classes, and crew. Among the passengers were some of the wealthiest individuals of their era. John Jacob Astor IV, whose fortune was estimated at around $87 million by 1912 standards, equivalent to several billion in today's money. Benjamin Guggenheim, Isidor Straus, co-owner of Macy's department stores. Their presence on board later became one of the arguments in favor of raising the ship. Wealthy families of the deceased wanted to recover bodies and personal valuables. In the night between April 14th and 15th, at approximately 11:40 p.m., the Titanic struck an iceberg in the North Atlantic at a speed of around 22 knots. The collision was glancing. The iceberg scraped along the starboard side, tearing open the hull plating across roughly 90 meters. Water began flooding 6 watertight compartments simultaneously. The ship's design could accommodate the flooding of 4 compartments and remain afloat. 6 compartments meant sinking was inevitable. The only question was when. Captain Edward Smith and designer Thomas Andrews understood this when they inspected the damage together around midnight. They had between 1 and 2 hours. There were not enough lifeboats for everyone on board, and even those left half empty, because in the early stages, nobody believed the ship was actually going to sink. At 2:20 in the morning, the Titanic disappeared beneath the surface. Of 2,224 people on board, 710 survived. The rest died. Most of them not from drowning, but from hypothermia in water that was approximately -2 degrees Celsius. Death at that temperature comes within 15 to 20 minutes. After the ship went under, it did not simply settle gently onto the seafloor. It fell. The fall from the surface to the bottom at nearly 4 kilometers depth took approximately 15 minutes. During that fall, the increasing pressure collapsed air pockets inside the hull one by one, deforming the metal from within. At some point in the descent, the exact depth remains unknown. The hull failed under the stress and broke apart. The bow and stern separated and hit the bottom independently, 600 meters apart. The bow drove into the seafloor sediment at roughly 30 to 40 kilometers per hour and buried itself several meters deep. The stern fell differently. It rotated during its descent, filled with water unevenly, and its condition after striking the bottom was fundamentally different. In the weeks immediately following the disaster, families of the deceased, the Astors, the Guggenheims, the Strausses, seriously discussed the possibility of raising the ship, or at least recovering the bodies. Several engineering firms received informal requests to assess the technical feasibility and cost of such an operation. All of them reached the same conclusion. The technology needed to work at that depth simply did not exist in 1912. The conversations faded quickly, and then the First World War began, and the Titanic receded from public attention. For the next 7 decades, the ship existed in a strange state of limbo. Everyone knew it was somewhere on the bottom of the Atlantic, but nobody knew exactly where. Search expeditions were mounted several times from the 1950s onward, all without success. The potential search area was too large, and the underwater search technology of the era was too limited. The United States Navy, through a classified monitoring program, had some data on the ship's approximate location derived from hydrophone tracking stations, but that information was classified and unavailable to civilian researchers. This is where Robert Ballard enters the story, and his story is considerably more complicated than the version most people know. Ballard, working at the Woods Hole Oceanographic Institution, had long wanted to find the Titanic, but lacked the funding for such an expedition. In the early 1980s, he approached the U.S. Navy with a proposal. The Navy would fund 2 search expeditions, during which Ballard would locate and document 2 sunken American nuclear submarines: the Thresher, lost in 1963, and the Scorpion, lost in 1968. In exchange, the Navy would allow Ballard to use any remaining time and equipment to search for the Titanic. The agreement was reached, and its details remained classified for years. Ballard revealed them publicly for the first time in 2008 in an interview with National Geographic. In the summer of 1985, Ballard found both submarines. What he saw on their remains, the catastrophic destruction caused by pressure, the evidence of how the crews had died, affected him so deeply that he has never described those findings in detail publicly. Having fulfilled the terms of his agreement with the Navy, he turned toward the coordinates where the Titanic was calculated to lie. Time was running short. Then, in the early hours of September 2, 1985, the cameras of the robot Argo passed over the boilers, and the entire team fell silent. They had found it. But the joy of discovery collided immediately with what Ballard described as a feeling of standing at the site of a catastrophe. The team held a brief memorial service on deck, and this became a tradition for every subsequent expedition to the Titanic. The following year, Ballard returned with manned submersibles and saw the ship for the first time, not through an underwater camera lens, but through a porthole. He described the experience as meeting a ghost. The ship was there, it was recognizable, you could almost reach out and touch it, and at the same time, it was already something completely different from the vessel that had left Belfast. In 73 years, something had happened to it that Ballard had not anticipated and could not immediately explain. The metal was covered in strange formations. Structures that should have been standing had collapsed. Sections of the interior that should have been preserved looked as though they had been crushed from within. The expeditions that followed brought 6,000 artifacts up from the debris field: crockery, jewelry, personal belongings, fragments of decoration. Every recovered object immediately became the subject of dispute. Who owned it? Who had the right to raise it? Where it should be kept? These legal and ethical questions eventually grew into an entire system of international treaties that today make any work at the wreck site nearly impossible. But that comes at the end of the story. For now, the essential point is this. By the time people first had the opportunity to seriously study the Titanic, it became clear that the question of why we have not raised it was far more complicated than it appeared. Depth is only one of the problems, and as it turned out, far from the most important one. Because before thinking about how to raise the ship, engineers needed to answer a question they first asked themselves in the 1980s, and that took nearly 40 years to answer definitively. What had actually happened to the metal? Chapter 2. Engineers versus the ocean. In 1996, the Walt Disney Company quietly closed one of the most ambitious and least known projects in its history. For several years before that, its engineering division had been seriously developing a plan to raise the Titanic, not for scientific purposes and not out of respect for the memory of the dead, but as a commercial attraction. The idea was straightforward and entirely dizzying. Raise the ship, tow it to a specially constructed port, and turn it into a tourist destination, generating hundreds of millions of dollars per year. Engineers worked through several technical concepts, ran the calculations, and at one point, the project looked almost achievable. Then the mathematics gave its final answer, and the project was closed. Not because the money ran out or interest faded, because physics turned out to be stronger than any budget. The history of attempts to raise the Titanic is a history of how one by one the most logical and technically grounded ideas shatter against the reality of deep water engineering. Each plan began with compelling logic, passed through a stage of detailed calculation, and ended with the same conclusion. To understand why, you need to look at the plans themselves, not in general terms, but in enough detail to see exactly where physics says no. The first idea that occurs to anyone who hears about a sunken ship is air. Ships float because there is air inside them displacing water. If you pump the water out of a flooded hull and fill it with air, it should rise. This principle is genuinely used to raise small vessels and submarines at moderate depths. The logic seems unassailable. The first serious discussion of applying this method to the Titanic took place as early as 1914, less than 2 years after the sinking, when memories of the disaster were still fresh, and several engineering firms were actively seeking ways to profit from a story that had not left the front pages. The idea at the time looked like this: lower flexible pipes to the bottom, fix them inside the hull, and begin forcing compressed air in under enormous pressure, gradually displacing the water from the compartments. As the air fills the hull, the buoyancy force grows, and at some point it exceeds the weight of the ship, and the Titanic begins to rise. Engineers of that era immediately hit the first and most obvious obstacle: the water pressure at a depth of 3,800 meters. To force air into a compartment operating under 380 atmospheres of pressure, the compressor must generate pressure exceeding that value. Otherwise, the air simply will not enter. The weight of water outside will push it back. To understand what 380 atmospheres means in physical terms, it helps to use a comparison offered by American oceanographer John Delacamp, who specialized in deep water operations in his lectures on underwater engineering. He suggested imagining that a weight of approximately 4 kilograms is pressing simultaneously on every square centimeter of your body. Multiply that by the surface area of the human body, around 17,000 square centimeters, and you get a total pressure of roughly 68 tons. That is what the water exerts on any object at the Titanic's depth at every moment. A hose lowered to that depth without special reinforcement will be crushed instantly, like an empty plastic bottle squeezed in a fist. A compressor capable of sustaining pressure above 380 atmospheres continuously for the days or weeks needed to pump out a hull of many thousands of tons did not exist in 1914, and building one would require colossal investment, even by modern standards. But suppose for a moment that this technical problem could be solved. Suppose the right compressors and pipelines exist. Then a second question arises: would the hull itself survive? The metal of the Titanic has spent more than 100 years in salt water. What happened to it over that time will be addressed in full in the next chapter. For now, it is enough to say that the answer radically changes every calculation for every method of raising the ship. But even setting aside the condition of the metal and looking only at hydrodynamics, the air method runs into a third problem that engineers did not immediately notice. As the hull begins to rise, it passes through different layers of water at different pressures. As it ascends, the external pressure drops and the air inside expands. This means the ascent becomes extremely difficult to control. At a certain stage, the ship may begin rising uncontrollably, accelerating as it goes. If the hull has weaknesses, and after 100 years on the bottom it certainly does, the sudden pressure differential during an uncontrolled ascent will destroy the structure. Simply put, a ship that survived the fall to the bottom might not survive the rise back to the surface. The second major category of ideas involves mechanical lifting, cables and cranes. This seems even more obvious. Attach cables to the hull, lift with sufficiently powerful cranes. This is precisely the approach that Walt Disney's engineers were developing in the 1990s, and this is where the mathematics proved most merciless. Start with weight. The empty hull of the Titanic weighs approximately 46,000 tons. Add to that the weight of the seafloor sediment that has literally bonded to the lower portions of the hull over decades. The bow alone has sunk roughly 6 meters into the seabed. The force required to tear it free significantly exceeds the weight of the metal alone. The sediment creates a powerful suction effect, similar to a foot stuck in bog mud, but on a scale of tens of thousands of tons. Norwegian engineers from the firm Stolt Offshore, who ran computer simulations of a lifting operation in the early 2000s, concluded that the initial force needed to break the bow section free from the seabed exceeded 100,000 tons. For comparison, the most powerful floating crane in the world at the time of those calculations, the Dutch vessel Tielf, had a lifting capacity of approximately 14,200 tons and operated at depths of no more than a few hundred meters. The gap between what is required and what exists is roughly sevenfold, even before accounting for the factor of depth. Depth introduces its own set of problems. A cable connecting a crane on the surface to an object at 3,800 meters must bear not only the weight of the load, but its own weight at that length. Steel is a heavy material, and a 4-kilometer cable weighs several dozen tons by itself. As cable length increases, its own weight becomes a significant fraction of the total load on the crane. This means that even if a crane could technically lift the Titanic from a depth of 100 meters, the same operation at 4 kilometers requires fundamentally different engineering solutions. But the main problem is neither weight nor depth. The main problem is water movement. The Norwegian engineers who modeled the lift on supercomputers documented an effect that destroyed all the calculations. When a large object begins slowly ascending through the water column, it inevitably starts to swing. Water at great depth is relatively calm, but as the object approaches the surface, currents grow stronger. A hull being raised on cables begins responding to those currents, swinging, rotating, striking against the cables. No dynamic positioning system in the world is capable of controlling this process with the precision needed for the safe lifting of such an object. According to the Norwegian team's calculations, the probability of losing control of the load and damaging the lifting vessel during such an operation exceeds 90%. 90% is not a technical risk that can be insured against. It is a near-guaranteed catastrophe. Understanding these limitations gradually shifted the conversation from raising the whole ship to raising parts of it. If the whole Titanic cannot be raised, perhaps the most valuable section can be extracted. The bow, which has better preserved its form and contains the most recognizable elements of the ship. This question became the next arena for engineering experimentation, and it is where the most unconventional ideas entered the story. A Danish inventor proposed filling the hull with millions of plastic balls. a British engineer proposed freezing the water around the ship with liquid nitrogen. Both projects found investors, both underwent serious technical calculation, and both ended the same way, but for reasons their authors had not anticipated. Chapter 3. The most outlandish ideas in engineering history. In 1964, a Danish inventor named Carl Kreuer raised a sunken ship from the floor of Kuwait's harbor by pumping millions of small plastic balls into its hull. The ship floated. The method worked. Kreuer received a patent, entered the history of salvage engineering, and spent the rest of his life convinced that his idea would one day be applied to the most famous ship in the world. When enthusiasts of raising the Titanic began seriously studying his method in the 1970s and 1980s, it seemed for the first time in decades that a genuine solution might be within reach. The calculations looked convincing. The physics did not contradict it. Investors expressed interest. And then someone counted the cost of the balls. The history of unconventional proposals for raising the Titanic is a history of how human ingenuity repeatedly runs not into the laws of physics, but into economic reality, and into one specific problem whose existence nobody suspected until scientists discovered it. But in order. Kreuer's idea, as applied to the Titanic, looked like this. Polypropylene balls a few centimeters in diameter would be pumped through pipelines into the compartments of the hull. Polypropylene is lighter than water. Its density is approximately 0.9 grams per cubic centimeter compared to 1.025 for seawater. This means each ball creates a small upward buoyancy force. Millions of balls create a combined buoyancy force sufficient to float the hull. No high-pressure compressors, no cables, no cranes, just a light material displacing heavy water. In principle, brilliant. A team of engineers who studied the method in the late 1970s ran preliminary calculations on the volume of balls needed to generate sufficient buoyancy. The result was impressive. Raising the bow section of the Titanic alone would require approximately 180 billion balls. This was not in itself an insurmountable obstacle. Producing polypropylene balls in any quantity is technically possible. But then the engineers looked at the second question. Would the balls survive the pressure at 3,800 meters depth? A pressure of 380 atmospheres will crush a standard polypropylene ball instantly. It will collapse on the way to the bottom, never reaching its destination. This means the balls must be not just light, but capable of withstanding extreme pressure while retaining gas inside. That requires either very thick walls or a special material. Both options sharply increase the cost of each ball. Engineers presenting calculations in the journal Ocean Engineering in the early 1980s concluded that 180 billion balls of the required quality would cost several billion dollars, roughly 20 to 30 times more than the estimated total value of the ship and everything on it. The project was deemed technically feasible and economically senseless. Before closing the ball idea entirely, one more problem deserves mention, one that its advocates preferred not to emphasize. Even assuming the balls could somehow be delivered into the hull's compartments, the logistics of doing so presented a challenge comparable in difficulty to the lifting operation itself. The ship is broken in two. Its interior spaces, after a century on the bottom, consist of a labyrinth of collapsed structures, blocked passages, and deformed bulkheads. Getting balls into every compartment would require either creating new openings in the hull or finding existing routes inside. Either option demands years of preparatory work using deep-water submersibles. Around the same time that engineers were working through the ball calculations, a British engineer named John Pierce proposed an idea that seemed even more fantastical at first glance, but had a certain internal engineering logic. Pierce proposed freezing the water around the Titanic using liquid nitrogen, creating a single monolithic block of ice. Ice is less dense than water, 0.917 grams per cubic centimeter. If a sufficiently large block of ice were formed around the hull, the entire structure, ship plus ice, would float to the surface by virtue of the density difference. By the accounts of his colleagues, Pierce was a methodical man, not given to fantasy. His idea was grounded in real physical calculations. The volume of ice needed to provide sufficient buoyancy given the Titanic's weight came out, by his calculations, to several 100,000 cubic meters. That is enormous, roughly equivalent to several large stadiums. Creating that volume of ice would require pumping a colossal quantity of liquid nitrogen into the area around the ship through a pipeline system and allowing it to evaporate, drawing heat from the surrounding water. Here, the plan ran into its first serious obstacle, the cost of nitrogen. Liquid nitrogen is relatively inexpensive in small quantities, but producing it in amounts sufficient to freeze hundreds of thousands of cubic meters of water at 4 kilometers depth would require industrial facilities comparable to a major chemical plant. Cost estimates range from several billion to tens of billions of dollars, depending on the assumptions used. This alone made the project economically impossible, but there was a second problem that Pierce's calculations did not fully address. The metal of the Titanic had spent a century in cold water. The temperature at that depth is about 2 degrees Celsius, already extremely cold. Creating a block of ice would mean sharply reducing the temperature immediately around the hull, and then, during the ascent, a sharp increase in temperature as the structure passed through progressively warmer water. Corrosion-weakened metal, subjected to a temperature swing of that magnitude, from -10 to +20 and back again, would almost certainly crack. Materials scientists consulted by the organizers of several expeditions were unambiguous on this point. The high sulfur steel of the early 20th century, already made brittle by decades of corrosion, would simply disintegrate under such thermal stress. Beyond these two main unconventional projects, various other less fully developed ideas appeared at different times. One American inventor proposed using magnets in the 1970s, lowering powerful electromagnets to the hull, attaching them to the steel, and pulling upward. This idea dissolved against a simple observation. Steel with a high sulfur content, which is what the Titanic's hull consists of, magnetizes poorly. Moreover, a century of corrosion had altered the crystalline structure of the metal to the point where its magnetic properties had become entirely unpredictable. Another project involved specially designed gas-filled synthetic floats, an upgraded version of Croyer's idea, but ran into the same pressure and cost problems as the original. By the mid-1990s, most serious engineers had converged on a single conclusion. Raising the whole ship was impossible by any known method. Too heavy, too deep, too fragile. It was precisely at this moment that the conversation shifted. What if the ship were not raised whole, but cut into manageable sections and brought up one at a time? This idea seemed more realistic, and it led to one of the most unexpected discoveries in the entire history of studying the Titanic. A discovery that had nothing to do with engineering or hydrodynamics, but that permanently closed the question of raising any part of the ship. Because when scientists looked carefully at what the metal of the hull had actually become on the ocean floor, they found something whose existence nobody had suspected. Something that had transformed the Titanic from a sunken ship into something fundamentally different. Chapter 4. The Bacteria That Eat History. In 1991, microbiologist Roy Cullimore from the Canadian Museum of Nature descended to the Titanic aboard a submersible and collected samples of the strange brown formations covering the ship's hull. He was not an engineer and had no interest in questions of salvage. He was interested in something else entirely. What exactly was growing on the metal of the sunken vessel, and how? When he examined the samples under an electron microscope several weeks later, he saw something that initially seemed like an experimental error. The metal was literally teeming with living organisms. Not algae, not mollusks, bacteria. Colonies of bacteria that were not merely living on the surface of the steel, but actively destroying it, using iron as a food source. This discovery overturned everything scientists understood about what was happening to the Titanic on the ocean floor. Before Cullimore, researchers thought of the ship's corrosion as a chemical process, the slow oxidation of metal under the influence of salt water, predictable, calculable, manageable. After Cullimore, it became clear that something entirely different was occurring. The ship was not simply rusting, it was being eaten. To understand the scale of what Cullimore found, you first need to understand what rusticles are, those brown formations that cover the hull and that all early expeditions had taken to be simply beautiful, if troubling, signs of corrosion. The word rusticle was coined by Ballard himself during his first dive in 1986. He formed it from the English word rust by analogy with icicle. The name stuck and entered scientific usage. Rusticles do look like icicles, long up to a meter or more in length, brown or rust-orange formations hanging from bulkheads, railings, and deck edges. They are so fragile that the lightest touch from a submersible's manipulator arm causes them to disintegrate into a cloud of reddish dust that hangs suspended in the water for a long time, degrading visibility. But their appearance is deceptive. A rusticle is not simply a clump of rust. It is a complex biological structure. Analysis of samples by Knorr and subsequent researchers showed that a rusticle consists of multiple layers, each populated by specific microorganisms. The outer layer is relatively stable iron mineral compounds. The inner layer is a living colony of bacteria actively working the metal. Between them are transition zones with varying chemical composition and varying microbial species. In its structure, a rusticle more closely resembles a living organism than an inorganic deposit, and this is precisely how scientists began treating it after Halomonas' work. The bacteria found in rusticles belong to several different species, some of which were discovered on the Titanic and have not been found anywhere else. In 2010, Spanish microbiologist Lourdes Ortiz announced the discovery of a new bacterial species isolated specifically from the Titanic's hull. She named it Halomonas titanicae in honor of the ship. This bacterium belongs to the group of iron-oxidizing microorganisms. It obtains energy by oxidizing ferrous iron to ferric iron. In effect, the metal surface is food for it. In her paper published in the International Journal of Systematic and Evolutionary Microbiology, Ortiz described the mechanism by which Halomonas titanicae and related bacteria degrade the steel surface. They secrete acids that dissolve the oxide film, which under normal conditions protects metal from further oxidation. Once the protective layer is stripped away, the next layer of metal is exposed to a new cycle of oxidation and consumption. The rate of this process initially seemed negligible. But when scientists ran calculations applied to the Titanic's entire hull, its surface area spans several thousand square meters. The numbers were alarming. According to estimates published in Halomonas' work and subsequently refined by other researchers, bacterial colonies destroy between 100 and 200 kilograms of metal per day across the entire hull. That means in a single year since the ship's sinking, bacteria have consumed between 40 and 70 tons of metal. Over more than 100 years, between 4 and 7,000 tons. This is not an abstract figure. It represents roughly 10% of the total weight of the steel hull, converted into rust dust and settled on the floor of the Atlantic. But this is still not the complete picture. Beyond biological corrosion, the metal of the Titanic has another fundamental problem rooted in the technology used to produce it. In the early 20th century, steel for large ships was smelted using methods that are now considered obsolete. The pressure to produce enough steel quickly and cheaply for a vessel the size of the Titanic led metallurgists to use processes that resulted in elevated sulfur content in the finished metal. Modern steels contain no more than 0.005% sulfur. In the Titanic's steel, according to analysis of samples conducted by metallurgist Timothy Folk at the National Institute of Standards and Technology and published in the journal JOM in 1998, sulfur content was approximately 0.069%, roughly 14 times higher than the modern standard. Elevated sulfur content creates inclusions of manganese sulfide in the metal's structure, microscopic deposits that act as stress concentrators. Under normal conditions, this makes the steel more brittle at low temperatures, a property that, in the view of most researchers, played a fatal role in the collision with the iceberg. The hull plating did not deform, it fractured. But 100 years later, this same property acquired a new significance. Sulfide inclusions are the preferred starting points for corrosion. Bacteria begin their work around them first, because sulfides are chemically reactive and more readily oxidized than pure iron. The result of the interaction of all these factors, originally brittle steel, a century of salt water, and biological corrosion, can be described in a single word used by every researcher who has worked with samples of the Titanic's metal: cardboard. The metal has come to resemble cardboard. It holds its shape as long as it is undisturbed, but at the slightest mechanical contact, it crumbles. Several expeditions that attempted to take samples of hull steel using submersible manipulator arms describe the same scene. The tool makes contact with a surface that visually appears to be a rusted but still intact steel plate, and it disintegrates into a cloud of rust dust, offering no resistance. Beneath the outer surface of the rusticles, there is often no metal at all, only a void, because the bacteria have already consumed it from within. This discovery permanently closed the idea of raising the ship in sections. If the whole Titanic cannot be raised, could the hull be cut into manageable sections and brought up one at a time? In theory, yes. Deepwater metal cutting is technically possible. Specialized tools exist that can operate at such depths. But as soon as engineers began working through the details of such an operation, they hit a fundamental contradiction. To cut the hull requires applying force to it, mechanical or thermal. Any force applied to metal with the consistency of cardboard will cause it to crumble around the point of contact. Instead of a clean cut, the result would be uncontrolled disintegration. The section intended to be raised whole would dissolve into fragments before lifting cables could even be attached. The only exception that some engineers pointed to was the bow section. The Titanic's bow, which settled into the sediment relatively gently compared to the stern, did retain more significant structural integrity. It became the last hope for those unwilling to completely abandon the idea of salvage. And it was precisely the condition of the bow that ultimately became the subject of the most important and most disturbing investigation in the history of studying the ship, an expedition whose findings permanently changed how we think about the Titanic. Chapter 5. The billionaire who said, "We are not going back." Victor Vescovo is not a man who is easily surprised. By 2019, he had already descended to the bottom of all 5 oceans, including the Mariana Trench, the deepest point on Earth, at 10,928 meters. He had seen underwater mountain ranges, sunken aircraft carriers, and places where no human being had been before him. His submersible, the limiting factor, was engineered to withstand pressures of 1,100 atmospheres, nearly 3 times the pressure at the Titanic's depth. Vescovo was prepared to see a damaged ship. He was prepared for the darkness, the limited visibility, the feeling of being present at a site of mass death. But when his submersible hovered above the Titanic's bow section and the high-resolution cameras began transmitting their images to the monitors, he did not speak for several minutes. The bow section was deteriorating significantly faster than any previous assessment had suggested. Not gradually, not uniformly, it was failing structurally, losing the load-bearing elements that had maintained its shape through the previous decades. The famous railings on the bow deck, the ones where Leonardo DiCaprio and Kate Winslet filmed their iconic scene in James Cameron's film, had collapsed. The officer's cabin on the starboard side had disappeared entirely. The roof of the captain's quarters had caved in. Where recognizable structures had still stood in 2005 during the last manned dive before Vescovo's expedition, there was now a mass of deformed metal, or simply nothing. The 2019 expedition was the first substantial manned dive to the Titanic in 14 years. During that interval, nobody had seen the ship close up, only images taken by autonomous underwater vehicles, which did not provide a complete picture. Vescovo and his team made 5 dives over the course of several days, systematically documenting the condition of both sections and the debris field. The overall conclusion they formulated upon returning to the surface was unambiguous. The ship was in significantly worse condition than had been believed, and the pace of deterioration was not slowing. It was accelerating. Marine biologist and deep-sea ecosystem specialist Claire Nouvion, who participated in the analysis of the expedition's findings, noted in comments to the scientific publication Deep Sea Research that the acceleration of deterioration has a systemic character. As outer load-bearing elements collapse, interior structures that had previously been sheltered by them come into direct contact with seawater and bacterial colonies for the first time. This means the process feeds itself. Each collapsing element exposes the next one, accelerating its own destruction. The ship is not simply crumbling slowly, it is moving toward a threshold beyond which the collapse will become cascading. Vescovo's statement that he would not return to the Titanic was received as a personal decision by a man profoundly affected by what he had seen. But it carried a deeper meaning. an understanding that any presence near the ship now itself accelerates its destruction. The water currents created by the submersible's engines act on fragile rusticles and weakened structures. The manipulator arms, even when not deliberately used to take samples, can accidentally contact a load-bearing element that is hanging at the edge of its tolerance. The paradox of studying the Titanic is that observation is gradually becoming part of its destruction. This paradox led to the idea that became the defining scientific achievement in the history of studying the ship, and that simultaneously concluded all hopes of physically preserving any part of it. In 2022, the company Magellan Limited, in collaboration with Atlantic Productions, carried out an operation that had no precedent in the history of underwater archaeology. Two autonomous underwater vehicles, named Romeo and Juliet, spent a combined total of more than 200 hours at the Titanic. During that time, they took more than 700,000 photographs of the ship, from distances of a few meters at every possible angle, covering every square meter of both sections and a substantial portion of the debris field. These images were loaded into specialized photogrammetric reconstruction software and processed over several months by computational systems, stitching individual photographs into a unified three-dimensional model. The result was a digital twin of the Titanic, a complete three-dimensional reconstruction of the ship, accurate to 1 millimeter. For the first time in the entire history of studying the vessel, scientists could see it whole, without the limitations imposed by darkness, poor underwater visibility, and the physical dimensions of submersibles. The digital model allowed a flyover from any direction, the ability to zoom into any fragment down to the level of an individual rivet joint, and the ability to look into spaces that no submersible could enter. What scientists saw in this model confirmed and amplified many times over what the Vescovo expedition had warned. When the 2022 digital model was overlaid with archival materials, photographs and video footage from expeditions in 1986, 1995, and 2005, and subjected to detailed comparison, the rate of change was significantly higher than even the most pessimistic previous estimates had suggested. The bow section had lost approximately 20% of its mass over 30-some years. This is not an abstract percentage. 20% of the mass of the bow section represents thousands of tons of metal converted into rust dust on the floor of the Atlantic. The digital model also allowed for the first precise description of the mechanism of deterioration. It became clear that the ship is not degrading uniformly across its entire surface. Deterioration follows specific pathways aligned with the structural lines of the hull, frames, bulkheads, rivet seam lines. It is precisely along these lines that bacterial corrosion is most active, because the metal there carries the greatest residual stress from the construction process. As these load-bearing elements fail, the adjacent hull plating panels lose their support and begin to bow inward or collapse. The specialists working with the digital model issued a forecast that subsequently appeared in all major publications on the subject. By the middle of the 21st century, roughly by 2050, the bow section of the Titanic will have lost structural integrity to the point where it ceases to be a recognizable object. The stern, whose condition is already significantly worse, may reach that point earlier. By 2100, what remains of the Titanic on the floor of the Atlantic will be a field of rust fragments and a silhouette pressed into the seabed sediment. All of this together, the accelerating deterioration documented by the Vescovo expedition, the scale of losses captured by the digital twin, the forecast of the ship's complete disappearance within a few decades, meant that the question of physical salvage had permanently lost its meaning. There was nothing left to raise. What remained of the Titanic could not survive any of the operations that would be required to extract it from the seabed. But precisely at this moment, when the story seemed to have reached its logical conclusion, it turned out to have one more chapter. Because, even if the metal of the ship had somehow been preserved in sufficient condition for raising, there remains one more barrier that has nothing to do with physics, chemistry, or biology. It is the law, and it is constructed in such a way that any operation involving the hull of the Titanic is legally impossible, regardless of the ship's physical condition. Chapter 6. The law is stronger than physics. In 2000, the company RMS Titanic Incorporated won a legal case that had been running for several years and that many observers considered a turning point in the history of the ship. The company secured the status of sole salvor of the Titanic, a legal term meaning the exclusive right to raise artifacts from the wreck site. It seemed that the ship now had an owner who could determine its fate. In reality, this decision opened a Pandora's box, from which, over the following 2 decades, emerged such a system of legal restrictions that today any operation involving the Titanic's hull requires the simultaneous consent of several sovereign states, passage through several independent licensing systems, and the fulfillment of technical conditions that are physically impossible to meet given the actual condition of the ship. To understand how this system developed, you need to start with a simple question: who actually owns the Titanic? The answer turned out to be considerably more complex than one might suppose, and this complexity ultimately became one of the principal factors making salvage impossible. The Titanic sank in international waters, at a point belonging to no state and lying beyond the exclusive economic zones of all coastal countries. Under the general principles of maritime law, an object lying in international waters has no state owner. It belongs to whoever found it and can establish a claim to it. This is precisely the principle on which RMS Titanic Incorporated built its original claim to salvor status. The company had participated in several expeditions, raised thousands of artifacts, and through American courts secured recognition of its rights. But in the early 2000s, the governments of 4 countries, the United States, the United Kingdom, Canada, and France, concluded that the ordinary principle of maritime law was insufficient for regulating relations with an object like the Titanic. Some researchers insist that the Titanic must remain untouched as a site of human death, and that any intervention constitutes a violation of the memory of the deceased. Others counter, the ship is deteriorating naturally and will disappear completely by the middle of this century. So would it not be better to preserve at least those parts that can still be saved while it remains possible? This argument has no definitive resolution because it brings 2 equally valid principles into collision: respect for a burial site and the preservation of historical heritage. But the reality is that by 2024, this argument had lost its practical significance. The physical condition of the ship, documented by the 2022 digital twin, makes the question of salvage rhetorical. There is nothing left to raise. The legal system built by 4 states makes the question of obtaining permission academic. Permission cannot be obtained. And the biological processes set in motion by the bacteria that Knorr discovered and Ortiz studied in detail make the question of preserving the ship on the seabed also settled. It will be destroyed regardless, simply by the ocean, not by human hands. In the end, the history of attempts to raise the Titanic turned out not to be a story about engineering ambition or legal barriers. It turned out to be a story about how human beings repeatedly encounter the limits of their capabilities, and how each time that limit appears not where they expected. In 1912, the limit ran along the strength of the ice that could not prevent the collision, and along the number of lifeboats that were not enough for everyone. In the century that followed, it ran along the depth of the ocean, the strength of cables, the cost of nitrogen, the fragility of metal, and the text of international agreements. Each time it seemed that the next technological step would allow it to be overcome. Each time it turned out otherwise. Today, the Titanic lies on the floor of the Atlantic, exactly where it lay on the night of its sinking. In darkness, under 400 atmospheres of pressure, surrounded by a field of debris that once formed part of the lives of 1,500 people. The bacteria continue their work. The metal continues to crumble. The rusticles continue to grow and fall away into the dark water. And the ship that was built as a symbol of human power and the invincibility of technology is slowly returning to the matter from which it was made: iron, water, silence,